These problems are going to focus on real-world applications of statistical probability, specifically converted into a percentage using either the chart, a calculator, or specifically Desmos. So our first example, we're looking at students taking an Algebra 2 test, and the class average score is an 80 in a standard deviation of 6 points. So we're always going to just start with labeling what we have. This is mu, and this is sigma. And so, when you read this question, you might say, well, why did they give us two things? What percent of the class would be expected to score between a 60 and a 90? Well, both of these are x's, and they're separate x's that we're going to have to find z-scores for. So the first z-score we have to find is we have to find 60 and then minus the mu of 80 divided by the standard deviation of 6. Always just start, if you ever get confused, just start with your formula. Of course, in statistics, in these kind of problems, we're just using this formula. So just start by seeing what you have, and in this case, it's all filled out. And for the z-score for the 90, similar situation, we would have 90 minus 80 divided by sigma. And so we look at that and are like, okay, we have two z-scores. They're obviously going to use the calculator. So I went ahead and typed them in. The first one is negative 3.3, repeating. And the second one, as you can see, is 1.6. So what does that mean? Well, I'll just draw you a little scenario based on what we learned earlier. If you take a look at the normal curve, right, we're trying to find the area under this curve, this being 0 standard deviations, or the mean. The first one, right, is at negative 123.3. So the first one's like here, and the second one is at 1.6, or about here. And the answer would be this area that lies between these two. Now, the beautiful thing about Desmos is Desmos can do this and even graph it. So what you would do is you'd go to functions. Okay, so you would go to functions and then go to distribution, go to normal distribution, click the CDF, find CDF, and you would just type in here negative 3.33, and then here you would type in 1.666. And you can even see it draws a picture. Now, to get that picture to draw, you're going to have to go to your wrench, change your x and y axis. Keep in mind that standard deviations only go from -4 to 4, and the y-axis sometimes will be at 20, so you just need to adjust those. And then I kind of zoomed it around. You can also zoom in if you want to see a better picture, but you can see it even draws that picture for us. Now, if you wanted to see how to do it on a calculator, I did make some videos. Please feel free to reference them. They just don't do this drawing, and it's not so user-friendly, but there is a video that I produced to show you how to do it on the TI-84. So the next question is, let's make sure we finish that one. So that comes out to a probability of 0.9517. So this comes out to 0.9517 as a probability, but it wants the percent. So you would multiply this by 100%, and if you multiply this by 100%, you get that 95.17% of the class would be expected to score between a 60 and a 90 on this particular test, given these statistical measures. So that's pretty good. I mean, that shows you that almost everybody will be in this between these values. So using the same information, what percentage of the class would be expected to score above a 95? Using the same formula, right? We're just always going to be trying to see how things fit into here. And just like in the previous part A of this, this value here is x. So our z-score would be 95 minus the average, which was 80. That was found up here in the original problem, and then divided by the standard deviation of 6 found in the original problem. So we first find the z-score, and then we just need to make sure we understand what the question's asking so that we can type it into Desmos correctly. So down here, we would just put in 95 minus 80. Don't forget, don't hit division here, because you see that's only dividing the 80. Right, you want to select the whole thing and divide. That's because there is a set of parentheses there, which will be important in the next problem. And so then we get 2.5 as our z-score. So keep in mind, this is asking for the score above. And so when you go into Desmos, you're going to want to for this particular problem, you're going to want to go to distribution, normal distribution, turn this on, and then you want it above. So the z-score is 2.5, and the maximum is infinity. Now, if it's not already there, it was there for me. You can actually type it in, which is awesome, and it will interpret that as infinity. So you can see that the probability is 0.0062, right? So 0.0062 then has to be multiplied by 100% to get the expected amount of students that had above a 95 on this test. And that would come out to 0.62, just move the decimal place over to, percent of students would be expected to have a score above a 95 on this particular test. So keep in mind that if you have a grade above a 95, it's statistically very rare, especially on a test that is statistically balanced, meaning in terms of averaging and making a test statistically balanced. Okay, so that's the overall idea. Now, don't forget, you can also use the chart for this problem, because when you look at the chart, it's going to give you the score below, but you can easily find 2.5, right? 2.5 is right here. Now, that's going to give you only the amount below. So remember, the little way to deal with this is if I need above 2.5, I do the opposite. Opposite is negative, so I'd look at the negative chart. And you can see right here that 2.5 would be, hey, the exact same number, 0.062. Notice it is the exact same number as we used for Desmos, so it's valid. And keep in mind that if you needed to go below a number, like let's say you need to know below -2, this does give you below, but if you wanted above for a negative z-score, you would use the positive side. So in this particular problem, again, just to recap, this value is giving me what is below. You could subtract from 1, or you could flip the sheet over and look at the negative and get the actual value that we got right here from Desmos. It's the exact same value. And again, just to reiterate it, there it is. So the chart's valid. Don't forget that chart is given to you on SOL day, and it is a valid thing to use, especially if you just want to look at above or below. Now, to do between, you would have to look up these values on the chart twice, and then subtract the smaller value from the larger value, and you would get, in fact, the same amount. That's a little more cumbersome. That's why I always like to show you the technology as well. All right, in our next problem, we're going to use the same formula, but for a different reason. Let's take a look. A new tech product is being scheduled to be released. The company's statistical research department showed that the average lifespan of this product should be 2 years. The company is confident that only 1% of the product will fail on delivery. So let's start with our formula, right? Our formula is saying, hey, we're talking about normal distributions, and we're talking about z-score. So we have this. And then once we do that, we start trying to fill it out. So we realize that it clearly gave us the average lifespan of 2 years. So this is mu. So we know that. And then it starts to get a little bit confusing. We do know, so that we're not looking for it, we do know that they're asking for the standard deviation. So we don't have to fill in sigma. That will be still just sigma. And so the question is, how do I find x and z? Now, I think a lot of people zone in real quick that this is something to do with it. It does not just go into z. It needs to be converted using something called the inverse normal. Now, if you use the chart, you would take this number and divide it by 100, so you get 0.001. Oops, I think I did that one too many times. Sorry, 0.01. And you would look for that in the chart. And when you look for that in the chart, you would find an approximation, but the number is so small that you start to sort of get a little lost. I'll show you. So looking at the chart, you can see that, 0.01, and actually, we really lucked out. We actually, we're trying to find it in here. And we get pretty close, right? But we don't actually get the value, right? 0.0107, and then it skips to 0.064. So the best we get is -2.30. -2.30 is the closest thing. Oh, oops, oh, here we go. There it is. That's the closest value, 0.0012. So -2.32. Now, to use Desmos, let's take a look at how that works. What we're going to do is we're going to go into Desmos, and we're going to go to functions and go to inverse CDF, meaning we're going to inverse the normal to give us a z. So we also have to put inside of that what we're inversing. We're inversing the normal distribution. Students will always ask, well, why do we have to do that? Well, later in other statistics classes like AP Statistics, there are all these other ones that we're not going to be doing. We're only focusing on this in Algebra 2. So within the normal, you're going to put 0 and 1 representing the mean and standard deviation. And then you have to come out of the normal. Notice the parentheses. You have to come out of it and put here the percent as a probability. So you can type in 1 divided by 100 if you want, okay? Or you could type in the actual value, which is what we looked up on that chart, which was 0.01. And notice it's the exact same value, but it gives us some more decimal places. So the chart's valid. It's very valid, but this is more accurate to decimal places. So this comes out to, this converts 1% to negative 2.326. And then the problem is, especially in this problem, students are like, well, I have two variables right now. I don't know what x is. And this is very subtle. I want you to notice that sometimes the critical reading skills really come in. It says we have a new product, okay? And that product we're trying to determine when when and if it will fail on delivery. So the fail on delivery means that what would you expect the lifespan to be? So do you see how that's subtle? And that's just reading between the lines here and reading the problem critically. Fail on delivery means that it will operate for 0 years. So we put a 0 in there. Let's clean this up and simplify it. So we have negative 2.326, and that is equal to negative 2 over sigma. And now we have to solve this using the reverse order of operations that we have been talking about in Algebra 2 the whole year. So we look at this problem, and we don't have addition or subtraction because the 0 sort of got rid of it, and plus that would have been in a parentheses. But we do have multiplication, and remember, treat sigma as if it were an x. So what you would do is you would multiply by sigma to get rid of it here, and then when you multiplied it over here, you would be able to solve. So we have negative 2.326 sigma is equal to negative 2, and so then you would simply divide by negative 2.326 on both sides, giving you the question, what the question actually asked. And so that would give us a sigma value. I'll have to type it in the calculator. So let's see here. So sigma would be, sigma would be 2. Got to go in a new spot. 2 divided by 2.321, which is 0.862 years. 0.862. And don't forget to use units. Years is our expected standard deviation of this new product. All right, so let's say the company, and this is why statistics is so important. Let's say the company was able to get it down to 0.5% of products failing on delivery. You would think that this would just double, right? Because all I did was take this, cut it in half, so you'd think that the standard deviation would just get better by that factor. But remember, when you do this equation, the 1/2 is not what goes into z. You have to convert this, right? You have to convert it, and then it can go into z. So using Desmos, since we already have it in here, we'll just go up here and adjust the normal distribution to represent a value of, again, what we're looking for here is 0.5 divided by 100. And so you can see it doesn't actually change the z-score that much, okay? So negative 2.56, negative 2.576, yeah, 76. So to use that chart again, we would have to look for 0.5 divided by 100, which would be 0.005. Let's see if it works. And you can see it right here. And this is where we really start to get into trouble. It's actually in the chart 3 times, right? And so the question is, which one do we use, right? And so actually that's the wrong value because that's 0.00. I need to find 0.005. So let's look real quick. We'll find it, try and find something close at least. It looks like we're getting close right there, and that's the closest we can find. So negative 2.60. And so you can see how that does it, but it's not as accurate as this value here. And that's why, of course, using technology really helps. So now that we found this value again from Desmos, getting this nice accurate z-score approximation, we're going to have x as fail on delivery, so 0. The mean was 2. We're looking for the new sigma with this improved level of quality. And so we're still going to multiply by sigma on both sides. Okay, and that'll give us negative 2.576 sigma is equal to negative 2. And then, of course, we divide. So let's see, I still have that in there. I just need to update the z-score. So if we update the z-score to the new one, you can see it didn't change by much. And of course, I left those negatives out earlier because I knew they would cancel, but you can put them in or leave them out. It's up to you. I knew they would cancel, so it was sort of a superfluous thing to type in. But if you're one of those people who wants to see it, there you go. So now the new standard deviation is now 0.776, 0.776 years. So by really ramping up the quality, we didn't majorly change the standard deviation, which is where companies sometimes have to make a decision about whether or not ramping up the quality is really going to increase what they're after for monetary. It costs a lot of money to increase that quality. So is it worth it if the standard deviation is only changing by that much? And that's what statistics does. It helps companies make decisions like that.